Imagine you wake up one morning in 2020 and your team has accidentally stumbled onto something scientifically impossible according to current models. Nobody was looking for it specifically. Nobody expected to find something like this. But there it is on the data screen. A planet where no planet should logically exist. A gas giant orbiting so close to a dead star that it completes an entire year in just 34 hours. The discovery is so anomalous, so fundamentally wrong according to everything you understand about planetary systems, that you spend the next 6 years trying to figure out if your instruments made a mistake. They didn't. The planet is real, but how it got there remains an absolute mystery until a telescope, called James Webb, finally arrives in space and begins observations, giving you the answer you've been desperate to find. This is not a story about what we found. This is a story about how we carefully figured out what it all means and exactly why it matters. This is about the detective work of understanding an impossible world. The planet has an official designation, WD-1856b, but what matters is the context. It orbits something called a white dwarf, which is what remains after a star like our sun dies. Imagine our entire sun being crushed down to the size of Earth. All that mass, all that gravity, all that stellar remnant compressed into a sphere roughly the size of our planet. That's a white dwarf. It's incredibly dense. A teaspoon of white dwarf material would weigh as much as an elephant. Now imagine a gas giant the size of Jupiter orbiting this cosmic marble at a distance closer than Mercury comes to our sun, orbiting it so fast that a year on this world takes 34 hours. That's WD-1856b. The problem is straightforward and devastating. And when the star that became this white dwarf was still alive, billions of years ago, it went through a process called becoming a red giant. The star expanded. It swelled outward dramatically. If WD-1856b had been orbiting anywhere near where it sits today, the star would have simply engulfed it, obliterated it, vaporized it completely. There's no mechanism in planetary physics that would allow a world to survive such a catastrophe if it was already in such a close orbit. And yet, the planet exists. The observations are confirmed. The data is solid. It's definitely there. So the question becomes almost tormenting in its simplicity. How? For years, the scientific community had a puzzle. Two possibilities existed. Either the planet formed somewhere far away and migrated inward after the star had already died and cooled down, or there's something we don't understand about how stellar death works. The evidence couldn't distinguish between these scenarios. The planet was there, but its history was opaque. You could observe it, you couldn't understand it, not with the tools available in 2020, not even with the best telescopes humanity had built by 2023. Then James Webb launched. The most powerful space telescope ever built, the most expensive scientific instrument in human history. It arrived at its observation point 2 million miles from Earth, in the cold darkness of space, and began looking at the cosmos in infrared wavelengths that previous telescopes couldn't effectively access. Someone on a research team realized that Webb might be able to answer the question that had haunted planetary scientists for half a decade. They scheduled observations. They waited for the precise moments when the planet would pass in front of its star. They collected data from those brief 8-minute windows when the planet became temporarily visible. Around 260 degrees Fahrenheit. That number might not sound remarkable, but against the backdrop of what we know about planetary cooling, that temperature becomes a revelation. If this planet had been orbiting this white dwarf for billions of years, it should be much, much colder. The white dwarf provides only a faint trickle of heat compared to what a living star radiates. A planet sitting in that faint light for eons should have cooled down to near absolute background temperature by now. Every physics textbook says so. Every simulation confirms it. But this planet is warm. It's still glowing with internal heat. That can only mean one thing. It hasn't been there for billions of years. The implications cascaded outward like dominoes through the scientific community. If the planet arrived there recently in cosmic terms, within the last few million years, then something must have moved it from wherever it originally formed. The leading explanation involves what happens when you have multiple massive objects, all gravitationally pulling on each other in a planetary system. Over millions of years, these gravitational interactions can subtly destabilize orbits, nudging worlds out of their original paths. One planet gets flung outward while another gets pulled inward. When WD-1856b got pulled inward toward this white dwarf, when it spiraled down from its safer, distant orbit into that impossibly tight configuration, something dramatic and profound happened at the gravitational level. The white dwarf's immense gravity, concentrated in such a tiny, dense object, began kneading the planet from the inside out. Imagine holding a rubber ball in one hand and the hand of your gravity field, pulling it in different directions as the planet orbited. The side of the planet facing the white dwarf experiences stronger gravitational pull than the far side. This creates tidal forces. The planet gets stretched and compressed repeatedly as it moves through even slightly non-circular parts of its orbit. This internal flexing, this constant kneading and reshaping, generates enormous amounts of friction. Friction at the molecular level becomes heat. Heat is what Webb detected. Heat that hasn't yet dissipated into space because the migration only happened relatively recently in astronomical terms. The planet is still glowing from a trauma it experienced only millions of years ago. A coal pulled from a fire continues radiating heat long after it leaves the flames. WD 1856b is still radiating heat from its migration, still carrying the thermal signature of a dramatic orbital rearrangement that's almost current events by stellar standards. This discovery proves that tidal heating can keep planets warm for extended periods, even in systems where stellar radiation is minimal. For planets close to dead stars, tidal heating becomes the dominant heat source. It's a mechanism that transforms worlds. It can trigger internal processes that would otherwise be frozen. It can generate geological activity. It can potentially power chemical processes in the planet's atmosphere. But WD 1856b's warmth isn't just a measurement. It's a window into the internal dynamics of a world undergoing dramatic transformation. But Webb detected something else, something that adds another layer to the story. Methane, organic compounds, haze, an actual atmosphere. Before this observation, nobody had ever detected an atmosphere around any planet orbiting a white dwarf. The fact that one exists around WD 1856b is remarkable enough, but the specific composition, hydrocarbons and organic chemistry, tells you something profound about planetary resilience. This atmosphere has been with the planet since its formation. It orbited with the planet when it was far from its star, in a cool, safe zone where such chemistry is common. It survived the star's death. It survived the star's transformation into a white dwarf. It survived the traumatic migration inward. It survived the tidal flexing that should have torn the planet to shreds, and it's still there. Still readable, still recording the chemical signature of a world that went through catastrophe and lived to tell the tale. Think about what this means at a fundamental level. A gas giant survived its star's death. It's not theoretically possible according to outdated models, but it's observationally confirmed. The data is there. The planet is real. The atmosphere is real. The temperature measurement is real. This isn't simulation or educated guess. This is observation of an actual world that made it through exactly what Jupiter and Saturn will eventually face. Here's where the story becomes personal to us. In approximately 5 billion years, our sun will begin the process that the white dwarf star already completed. The hydrogen fuel in the core will be consumed. The core will contract, while the outer layers expand dramatically. Our sun will swell into a red giant, enormous and terrible, likely large enough to engulf Mercury, Venus, and possibly Earth itself. For a period that will feel eternal but is cosmically brief, the sun will be a dying star, radiating incredible heat, its atmosphere extending millions of miles outward. Then it will shed its outer layers into space. It will collapse into a white dwarf. And what happens to Jupiter and Saturn during this process has been entirely theoretical until WD 1856b gave us a real observational example. The planet tells us something hopeful. Not comfortable, not safe, but hopeful. Giant planets can survive. They can migrate into new orbits around the stellar remnants their stars become. They can carry their atmospheres with them. They can endure. That's not survival in any pleasant sense. The future is hostile and transformed. But it's survival nonetheless. A world that went through stellar death and remained essentially recognizable as a world. The precision required to make this discovery deserves profound appreciation because it reveals the cutting edge of what modern astronomy can achieve. Consider the challenge in concrete terms. An 8-minute observation window every 34 hours. Miss it, and you wait more than a day for the next opportunity. A faint signal from a planet orbiting a dim star 80 light-years away. The white dwarf is incredibly dim compared to normal stars, putting out far less light. The planet is also comparatively small. The signal of infrared radiation from the planet itself is barely distinguishable from background noise. Separating that signal from instrument noise, measuring exactly how much infrared light gets blocked during the transit, detecting specific chemical signatures in the atmosphere as starlight filters through it. As this required the combination of an enormous mirror collecting far more light than previous telescopes, infrared sensitivity in the exact wavelengths where planets radiate heat, a stable observing platform free from vibration and thermal fluctuations, and the ability to repeat observations across multiple planetary orbits to build up enough data for statistical confidence. James Webb is the only instrument in human history that can accomplish this particular work. No previous generation of space telescopes had the combination of capabilities required. Its massive primary mirror, made of precisely shaped beryllium segments, collects far more light than earlier instruments. Its infrared instruments are sensitive to wavelengths, where thermal radiation from distant planets can be detected. Its location at the second Lagrange point, 2 million miles from Earth, places it in an environment cold enough that the telescope itself isn't radiating infrared noise that would overwhelm the signals from distant objects. The thermal control systems keep the instrument at temperatures cold enough that photons from WD 1856b can be reliably detected and measured. The research team, led by Ryan McDonald at the University of St. Andrews with collaborators from Cornell University and other institutions, had to schedule observations carefully, anticipating the exact times when WD 1856b would transit its star. They accumulated data across months, gathering signal during multiple 8-minute windows, and building up a data set large enough to draw reliable conclusions with scientific confidence. Each observation session produced data that was processed and analyzed. Noise filtering was applied. Statistical methods were used to distinguish signal from background. Only after sufficient data had accumulated could the team publish conclusions in a peer-reviewed journal. This is what real astronomical discovery looks like. Not sudden revelation, but patient accumulation of precise measurements leading to understanding. The lead researcher, Ryan McDonald from the University of St. Andrews in Scotland, published the results in Nature in July 2026, a peer-reviewed journal named Scientists, Specific Methodology, Reproducible Observations. This is what real discovery looks like compared to the fabricated headlines that appear in clickbait space videos. Real science takes years. Real science involves patience and precision, and the willingness to wait for enough data before making claims. But the implications of this discovery extend far beyond this single planetary system. Every white dwarf system now becomes interesting in new ways. If planets can survive stellar death and migrate into new orbits, then the number of potentially interesting planetary systems increases dramatically. If planets can retain their atmospheres through this process, then the chemistry of these worlds becomes observable and analyzable. Scientists now have a confirmed example of a mechanism that was previously only theoretical, that opens entire new research directions. There's also the question of what else might be orbiting this white dwarf that we haven't detected yet. The migration that brought WD 1856b inward probably involved gravitational interactions with other bodies in the system. Are there other planets orbiting in different configurations? Are there smaller objects, asteroids or comets, still circling the white dwarf? What's the complete architecture of this system that has already been transformed by stellar death? Future observations might reveal more pieces of this puzzle. Each discovery would add significantly to our understanding of how planetary systems reorganize themselves in the aftermath of stellar catastrophe. In fact, Webb has already spent meaningful observing time studying white dwarfs more broadly, looking for debris disks, shredded planetary material orbiting dead stars. Roughly a quarter to half of all known white dwarfs show chemical signatures of this kind of debris in their spectra. Tiny traces of heavy elements like calcium, magnesium, and iron, elements that should sink deep into a white dwarf surface, appearing in the outer atmospheric layers. That suggests these elements are constantly being replenished by infalling debris. These systems tell a story of destruction. Planets and asteroids that orbited too close to the red giant or that got flung inward by chaotic interactions, got torn apart by tidal forces and rained down as debris onto the white dwarf's surface. But WD 1856b tells the opposite story, a story of survival and migration. Some planetary material makes it through. Some worlds don't get destroyed. They find new orbits and persist. Seeing both outcomes, destruction and survival, enriches our understanding of the full range of possibilities when stars die. For those who think about Earth's distant future, this discovery carries weight beyond mere scientific curiosity. Earth itself will be destroyed by the sun's red giant phase. That's virtually certain. But the outer planets might have a different fate. They might be reshaped by gravitational interactions. They might migrate into new orbits. They might survive in some form, transformed but recognizable. WD 1856b is proof that such survival is possible. Not guaranteed, but possible. That's something. Consider also the visual reality of this system. A white dwarf, despite being dead, still glows. It radiates leftover heat from its collapse. It appears warm orange, similar in color to our own sun, even as it slowly cools over billions of years. And orbiting this glowing ember is a gas giant 7 times wider than its star. Picture that. A massive world completing an orbit in 34 hours around a stellar remnant smaller than Earth. The geometry is almost inverted from what we're used to. The planet is larger than its star. The year is shorter than a day. The surface temperature of the planet glows with internal heat. It's an alien scenario, almost impossible to visualize if you haven't thought about it carefully. The broader scientific context also matters. Webb has been studying white dwarfs for a while now, looking at debris disks, shredded planetary material orbiting the stellar remnants. For many white dwarfs, you can detect the chemical signatures of planetary bodies that got torn apart by the dying star's gravity. calcium, iron, magnesium, heavier elements raining down on the white dwarf's surface. Those systems show destruction, planetary systems destroyed utterly by stellar death. But WD 1856b shows the opposite outcome. A planet that survived, that migrated, that retained its atmosphere. Seeing both outcomes, destruction and survival, gives scientists a much richer picture of the possibilities. Stellar death isn't uniform. Different systems have different outcomes. The question of planetary migration itself connects to broader mysteries in exoplanet science. Hot Jupiters have puzzled astronomers for decades. Gas giants found orbiting close to their stars in orbits of just a few days. This violates the standard model of planet formation. Giant planets should form far out where it's cold and there's plenty of material, but they end up close to their stars. How? Migration provides an answer. Gravitational interactions in multi-planet systems can destabilize orbits and send planets spiraling inward. Planet-planet scattering, it's called. WD 1856b appears to be an extreme example of this same process, but occurring around a star that had already died. The mechanism is proven, the physics is sound, the observational evidence is now available. There's also something worth appreciating about the timeline of discovery that reveals how science actually progresses. WDAS 1856b was first detected in 2020 using older space telescopes, NASA's TESS and the retired Spitzer Space Telescope. For 6 years afterward, the mystery remained stubbornly unsolved despite the best efforts of the astronomical community. No tool existed that could provide the answer. The planet was observable, but its history was locked away, inaccessible to current technology. Scientists could see the anomaly. They couldn't understand it. That's how real astronomy often works, frustrating, patient, waiting for the right instrument to arrive. Then James Webb launched. Its infrared instruments came online. Months passed as the telescope cooled down and calibrated. Then astronomers began submitting their observation proposals. Someone suggested that Webb might be able to answer the question that had haunted them for 6 years. The proposal was accepted. Observations were scheduled. Researchers waited for the precise moments when WD 1856b would pass in front of its star. They collected data from those 8-minute windows, repeatedly across multiple orbits, accumulating signals slowly but steadily. And finally, in July 2026, enough data had accumulated that the picture became clear enough to publish in Nature. That timeline, from mystery to answer, spanning more than half a decade. That's how real science works. Years of waiting, years of unanswered questions, generating papers and hypotheses. Then a new tool arrives, and suddenly the mystery becomes solvable. The question gets answered not through inspiration or luck, but through patience and the right technology at the right moment. That's not drama invented for clicks or artificially created urgency. That's the actual pattern of scientific progress. The atmospheric detection itself deserves special attention and deeper analysis. Transmission spectroscopy is the technique that makes it possible. When a planet passes directly in front of its star, an event called a transit, light from the star travels through the planet's atmosphere at an angle. That light gets filtered through the atmospheric layers. Chemical species in the atmosphere absorb specific wavelengths, creating dark absorption lines in the spectrum. Those absorption lines become chemical fingerprints identifying what gases are present. For WD 1856b, only the very edge of the planet crosses the stellar disk from our perspective, what's called a grazing transit. It's the briefest of interactions between planet and starlight. But that edge passage is enough to reveal atmospheric composition with remarkable detail. Methane, organic compounds, hazes similar in character to those found on Saturn's moon Titan. An orange-tinted haze, if you could somehow see it up close, wrapping an alien world in a veil of exotic chemistry. The atmosphere tells a story, a record of the planet's original formation and composition, preserved through stellar death and migration. The implications for future astronomy are deeply significant and worth careful consideration. If transmission spectroscopy works effectively for studying WD 1856b, the technique can be applied to other white dwarf planets. Some astronomers have specifically and seriously proposed that Webb represents the first realistic tool for searching for potentially habitable, Earth-sized rocky planets around white dwarfs. The mechanism is sound. The technique is proven. If such a world were found, if it existed in the right kind of stable, long-lived orbit, if you could detect biosignatures in its atmosphere, molecules like oxygen or methane in combinations suggesting biological origin, that would be revolutionary beyond measure. It would represent humanity's first confirmed detection of life around a dead star system. WD 1856b itself isn't habitable. Too massive, too close to the star, too hot, too hostile for any life as we understand it. But it proves something crucial. The observational technique works. The methodology is validated. The tools are proven. The path forward has been demonstrated. Future discoveries of smaller, potentially habitable rocky worlds around white dwarfs now become realistic possibilities, rather than merely theoretical dreams. WD-1856b is a proof of concept, a demonstration that if such habitable worlds exist around white dwarfs, humans now possess the technology to detect them and study their atmospheres in detail. That's transformative for the future direction of astrobiology and exoplanet research. There's also real beauty in understanding how nature solves problems. The universe doesn't destroy everything during stellar death. It reshuffles, it reorganizes. Planets get flung outward, orbits destabilize. But some worlds survive. They migrate into new configurations. They settle into new equilibria. It's violent and chaotic and utterly foreign to our experience. But it's also resilient in a way that's almost hopeful. Systems don't end cleanly, they transform. The broader context of James Webb's mission makes this discovery even more scientifically significant. Webb wasn't designed specifically to study white dwarfs and their planets. It's a general-purpose observatory built to study the universe across many different scientific questions and domains. Yet it's already proving invaluable for this particular research area. The combination of capabilities it possesses, massive mirror collecting far more light, infrared sensitivity detecting heat from distant objects, extraordinary stability in space, location far from Earth's thermal interference, happens to be exactly what's needed for detecting and characterizing planets around white dwarfs. This illustrates a broader truth about how science actually progresses. The most transformative discoveries often come from tools built for general purposes that end up being perfectly suited for problems researchers didn't anticipate when designing them. Webb was built to study many things: distant galaxies from the early universe, star formation in molecular clouds, exoplanet atmospheres around normal stars. But it's proving equally revolutionary for studying planetary systems around dead stars, revealing an entire class of worlds that were almost completely inaccessible to earlier astronomy. When you step back from the technical details and look at what this discovery actually means, you're looking at a window into the future of our own solar system. Not a comfortable future, not a pleasant one, but a possible one. Jupiter might see its star die. It might experience gravitational chaos as orbits destabilize. It might spiral inward or outward or settle into a completely new configuration. But if WD-1856b's example holds, Jupiter might survive. It might retain its atmosphere. It might continue to exist, transformed but recognizable, orbiting the white dwarf that was once our sun. That's not certainty about what will happen. That's not guarantee that Jupiter will survive. But it's more than we knew 6 years ago before this discovery. It's direct observational evidence of a possibility that we could only simulate in computers before. That's a fundamental shift in our knowledge. The discovery ultimately tells us something profound about the resilience of worlds and the persistence of planetary systems. Planets are tougher than previous models suggested. That survival is more possible than we imagined in the abstract. That stellar death, while catastrophic and violent and utterly transformative, doesn't necessarily mean the end of everything. Some worlds make it through. Some systems don't collapse into complete disorder, but instead reorganize and stabilize into new configurations. Some stories don't end in annihilation, but in transformation and continuation in different forms. That's a message worth understanding deeply. WD-1856b has been through experiences that would destroy most worlds. Its star collapsed. The star's outer layers expanded and then exploded outward. The planetary system was thrown into chaos. Yet the planet survived. It migrated. It settled into a new orbit. It retained its atmosphere. It's still glowing with internal heat millions of years later, still carrying the chemical signature of its original formation from the distant reaches of its stellar system. That's not survival in a comfortable sense. That's not life as we'd prefer it. But it's survival nonetheless, transformed, altered, living in a harsh new reality, but existing nonetheless. For our own solar system, this carries implications we should contemplate carefully. Jupiter and Saturn will face their own reckoning in 5 billion years when our sun begins its red giant phase. They won't be able to prevent it. They can't escape the gravitational cage they orbit in. But the example of WD-1856b suggests they might not be obliterated. They might experience chaotic orbital rearrangement. They might migrate inward or outward, finding new equilibria around the white dwarf that will be all that remains of our sun. They might continue to exist in some form, their atmospheres intact, their masses preserved, their existence continued if transformed. That's not the future we would choose if we had a choice, but it's a possible future nonetheless, and it's one where some form of planetary body persists. There's something almost poetic in how nature handles the end of stellar systems. It doesn't preserve things as they were. It doesn't allow comfortable continuation, but it also doesn't destroy everything utterly. It transforms. It reorganizes. It shuffles the pieces into new arrangements. Some pieces are destroyed. Rocky planets close to the star often get shredded completely, but some pieces survive and find new homes. That's the reality revealed by WD-1856b. That's what 80 light years of space is whispering back to us. Not a message of despair about death and destruction, but a message about resilience and transformation and the possibility of continuation in altered forms. When we look at that system, we're looking at something that will eventually be relevant to us in the most intimate way possible. Not in 5 billion years, but metaphorically in this moment. We live on a world that will eventually be destroyed by its star. That's not something to be afraid of. It's so far in the future that it's less relevant than worrying about anything happening on human timescales. But understanding that some form of planetary existence might continue beyond our star's death, that worlds can survive and transform and endure through stellar catastrophe. That's a message worth receiving from across the cosmos. That's what WD 1856b whispers across 80 light years of space in a voice made of heat and light. In methane molecules and organic chemistry and residual warmth from a migration that happened millions of years ago, a message that says planets can endure through cosmic catastrophe, worlds can transform and find new existence and survival, true survival beyond comfort, beyond familiarity, beyond what we would choose for ourselves, but survival nonetheless, is possible even at the end of stars. That's what WD 1856b tells us across the cosmos, written in the language of physics and chemistry and time itself.